Thermodynamics. Hardest part of this is definitely the definitions. So enthalpy change of atomization of a compound is, but let's think about this logically, right? Enthalpy change of atomization of a compound. What does that even mean? Well, if we're thinking about enthalpy change of a compound, well, so enthalpy change of 1 mole of a compound is converted to its gaseous atoms in the standard state. Well, all of these is in the standard states, every single one of them. So I guess you can get rid of that part because you already know it's going to be standard state for all of them. So enthalpy change of 1 mole of compound is converted to its gaseous atoms. Perfect. Enthalpy change of atomization element, enthalpy change of 1 mole of a compound is 1 mole of gaseous atoms is formed from an element in a standard state. Of a gaseous atoms formed from elements in standard state. So for example, this NaCl solid, sodium chloride solid, goes to Nag plus Clg. First, electron affinity. Enthalpy change of 1 mole of gaseous 1 minus ions is formed from 1 mole of gaseous atoms. Enthalpy change of 1 mole of gaseous 1 minus ions is formed from 1 mole of gaseous atoms. Og plus E minus from O minus G. Second electron affinity, enthalpy change of 1 mole of gaseous 2 minus ions formed from 1 mole of gaseous. Because this one, first electron affinity, enthalpy change of 1 mole of 1 minus ions from 1 mole of formed from 1 mole of gaseous atoms. Enthalpy change of 1 mole of gaseous 2 minus ions formed from 1 mole of gaseous 1 minus ions. O minus plus E minus from O2 minus. Perfect. Enthalpy change of hydration, enthalpy change from 1 mole of aqueous ions is formed from 1 mole of gaseous ions. Enthalpy change of 1 mole of aqueous ions formed from 1 mole of gaseous ions. So for example, Na plus gaseous from Na plus aqueous. Enthalpy change of solution, enthalpy change of 1 mole of a compound. 1 mole of solute is dissolved in enough solvent so that no further enthalpy change occurs on further dilution. Enthalpy change of solution, enthalpy change of 1 mole of solute is dissolved in enough solvent so that no further enthalpy change occurs on further dilution. NaCl solid to NaCl aqueous. 1 mole of solute is dissolved in enough solvent so that no further enthalpy change occurs on further dilution. What I recommend, if you still haven't memorized these like I have not memorized all of these, probably none of them, just keep going through it every day and you'll get it before the exam day. Bond dissociation enthalpy, the enthalpy change of all the bonds of the same type in 1 mole of gaseous molecules. Enthalpy change of all the bonds of the same type in 1 mole of gaseous molecules are broken. Cl2 gases to 2 Cl gases. Lattice enthalpy of formation. Enthalpy change of 1 mole of solid ionic compounds formed from its gaseous ions under standard conditions. Na plus gases plus Cl minus gases to form NaCl solid. So lattice enthalpy dissociation, enthalpy change of 1 mole of a solid ionic compound is converted to its gaseous ions under standard condition because the lattice enthalpy formation with enthalpy change of 1 mole of solid ionic compound is formed from its gaseous ions. So lattice enthalpy dissociation, 1 mole of solid ionic compound, instead of formed from its gaseous ions, is converted to its gaseous ions. Dissociated into gaseous ions. NaCl solid, R Na plus gaseous plus Cl minus gaseous. Lattice enthalpy is a measure of ionic bond strength. And there's two types of lattice enthalpy formation, lattice enthalpy dissociation, which I just went through. Lattice enthalpy dissociation, when 1 mole of solid ionic compounds converted, is complete dissociation to gaseous ions. And the enthalpy change, lattice enthalpy formation, enthalpy change 1 mole of a solid ionic compound is formed from its gaseous ions. Gaseous, right? Yeah, it's got to be gaseous. Perfect. So that's all the definitions you have to memorize. Now moving on to the actual content, because those are just expected to know. Two assumptions of Ionic model of a lattice assumes all ions are spherical and assumes the charges of the ions are evenly distributed across them. How to work out theoretical lattice enthalpy and what happens if you find it experimentally. But doing calculations based on purely ionic model of a lattice. And if you find lattice enthalpy experimentally, you're not going to get is different. The value you're going to get is different, and therefore evidence for most ionic compounds have covalent character. Again, I would even learn this flashcard because so many past paper questions. Because every year, thermodynamics always comes up, without doubt. It's like guaranteed to come up in paper 1. And instead of like confusing yourself with this, which would never ever ask you, What they would ask you is, a student got this value and you calculated the value. Why is the value different? You would say because it's got some covalent character. Therefore, the forces holding lattice together are stronger. And if it said why the values, what is the difference in values, and it's like difference by one, then you say they're purely ionic. But yeah, all you need to know is if there's a big difference or noticeable difference, just covalent character. But just learning that whole thing is just going to confuse you, and it's just unnecessary. Most ionic compounds have covalent character. This is really important because the positive and negative ions of the lattice aren't exactly spherical. Because the positive and negative ions aren't exactly spherical, the positive ions polarize the neighboring negative ions to different extents. Therefore, more polarization, more covalent the bonding. 3 things happen when a solid ionic lattice dissolves in water. I'm going to check if there's even a specification. What's this topic? Thermodynamics. So it says, define each of the above terms. Yep. Could short Born-Haber cycles. Yep. That's not even a flashcard to make. That's just a practice, which they love asking you. So just do all the past paper questions for that. Compare lattice entities. Yes. Define enthalpy change of hydration. Enthalpy of hydration. Yes. We've gone through that. That's it. So this lattice enthalpy. Again, I don't think we need to know these. No, we don't. It's not in the spec. Okay, why do in general do soluble substances have exothermic enthalpy solution? In general, this could definitely come up. Because substances generally only dissolve if energy released is the same or greater than the energy taken in. Entropy S, a measure of the number of ways that particles can be arranged. And yeah, I got the first part right. Number of ways particles can be arranged. And the number of ways energy can be shared out between the particles. So if it was just a 1-mark question, define and state what was meant by the definition of entropy, you would just say a measure of number of ways particles can be arranged. If it was 2 marks, then you say a measure of number of ways particles can be arranged and number of ways energy can be shared out between particles. Higher entropy means more disorder. More disordered the particles are. Substances tend to disorder. Why? Substances tend to disorder because they're more energetically stable when there's more disorder. And therefore particles move to increase the entropy. Reactions happen by the cells without addition of energy even when delta H is endothermic. Standard entropy of a substance. Entropy of 1 mole of a substance under standard conditions. Entropy of 1 mole of a substance. Entropy of 1 mole of a substance under standard conditions. And increased total entropy means feasible for a reaction to occur. Free energy is a measure of to predict whether a reaction is feasible. Reaction might happen by itself if delta H is less than 0. Again, they would never ever ask you this. What is free energy a measure of? And if we have a quick look at the specification, sure, it helps with understanding, but at this point in time, I need to just memorize the key stuff. And same with you guys. Yeah. So this is not useful. Perfect. Get rid of that. What happens when delta H is positive and delta HS is positive? Well, let's think about it. If delta G is delta H minus T delta S, we have to know that. Delta G is delta H minus T delta S. If delta H is positive and delta S is positive, delta G is going to be negative, right? So the reaction won't be feasible at some temperatures, but will be at high temperatures. If delta is negative and delta S is negative, then the reaction won't be feasible at lower temperatures, will be feasible at low temperatures but won't be feasible at high temperatures. One way to remember this is just think about, okay, positive, they're only going to be feasible at high temperatures because high temperature is positive. And then negative, they're only going to be feasible at low temperatures. Easy. And you can easily do that. That's perfect. If delta G is 0, then a reaction is just feasible. And how to find temperature at which a reaction just becomes feasible? Well, delta G is 0, therefore T delta S equals delta H.